Yeah, so let's take a look at the start to take a look at chapter 5 here. Okay. So chapter 5 takes us into hydro, and as is typical with the book, they take sort of a big picture stance first on what the annual production is. So hydro has sort of grown steadily. It's showing that annual production sort of peaked in a way a few years ago, and so hydro also kind of steadily continues to grow. At some point, you just run out of things to dam up, and you can't go any further. But what we're seeing here is hydro is sort of a base load. There's also some neat little maps showing this century or so old system in England for producing electricity. Fairly predictable. You're relying on rainfall, you're relying on topography. If it were not for the fact that the earth were lumpy and that water evaporated, none of this would work. So it's obviously the hydrological cycle that's driving that. And of course, the whole point here is to make electricity. There are also some neat little charts in the chapter that show you the heights of each one of these guys. Here's a nice little shot of a power station. I know we've talked about this a little bit in class, but for any power system, whether it's mechanical or electrical, what you're dealing with is the multiplication of an across variable with a through variable. So let's see if I can't get this guy up and running here. I'll give it a second to work. In the meantime, let me just type out what I'm talking about. Yeah, I'm not going to be able. Oh, wait, maybe. Hang on. Yeah, it won't work with the pen. All right. What I'm going to show you here, though, is critical to understanding hydropower. So, if we're looking at power, it always equals something like a force times a velocity, or a power equals current times voltage. So in this case, the power is obviously a scalar variable, doesn't have a direction. Force is a vector. I'm going to be a little more, that's one way to write it. I'm going to write it a different way too. The way you would write this in engineering format would be to put in a dot, because because force and velocity are both vectors. Current and voltage are also scalars, so you don't need a special symbol in there. So this is how you calculate electric or mechanical power. Electrical power. And the across variables are force and current, and the through variables are velocity and the through variables are velocity and current. Okay, so what I'm trying to do here is lay the groundwork for how you calculate hydropower. So in this case, for mechanical power, you're going to multiply force times velocity. More correctly, you're going to take the dot product of the two. If you are calculating electrical power, you're going to multiply current by voltage. In these systems, the across variables are force or voltage, and the through variables are velocity and current. Let's give these guys the right... So capital V for voltage, capital F for force. It's not always, sometimes it's lowercase. And typically, if you're writing a vector, you normally just make it bold and you don't make it italics. So I'm just going to use that convention. And then scalars are typically just italics. So to get power, you're multiplying some across variable by some through variable. So for hydro, which is also mechanical, what two things do you think you're multiplying together to get power? Because obviously we're sitting here looking at the textbook. That is a power dam. We are taking this mechanical energy sitting here upstream and turning it into the electrical energy downstream. So what might our two variables be here?
Would it be a matter of rotation of the turbine?
Just think upstream in the lake. And just before you get to the turbine, what's going on? You want gravity, yep, and the gravity is going to create what behind that dam? No, behind the dam,
Force.
it's actually going to create pressure or force. So the greater the pressure, so the higher the dam. This must be kind of a low dam. I don't actually see it here, but obviously at the surface of the water. Let's just grab something. So there we go, Hoover Dam. Right up here on the surface of the water, the pressure's zero. The pressure's 14.7 psi. Down here, though, the deeper we get, the pressure's enormous, and that's what you need to make power. There's your pressure. And then I think you mentioned velocity too. What you're actually looking at is the mass flow rate. So the more pressure you have and the faster water is flowing through that system, the more power you have. You got to have both. And so, of course, pressure is the across variable, and mass flow rate is the rate. It's kilograms per second. And we can do it. we'll do a dimensional analysis. That's not, what I wrote here is not exactly right, but it's the right way to think about it. Okay. Here you can see an ecological feature. So if you are a fish and you have been swimming back and forth to your spawning or breeding grounds for several 100,000 years, and all of a sudden there's a dam in the way, what do? Well, you hope the humans are nice enough to put a little ladder in for you. So this is a way for the fish to swim back upstream, find their spot, and do their thing. Here again, world output, and this is in terawatt hours. You could do a little, extrapolation. Say, well, gosh, is there more? Is there more energy to give? One kind of neat back of the envelope. And this is kind of the fun thing that you can do with some of the math in this course. Is Hugh Jesse, our former facilities director, calculated that if you took the Mansfield Library, all 4 or 5 stories of it, and put it at the M and filled it with water once a day, you could run the whole university. So again, what you've done by putting it up at the M, you've created more pressure, and by giving it the distance from the M to come downhill, you're creating the mass flow rate. So you've given it, and sometimes you might see it in the book. It'll be written. The engineering word is head. Head of pressure. How much head of pressure? So sometimes P, rather than being measured in pascals, is measured in it's just called head of pressure. So that's another kind of back of the envelope to say, gosh, just stick that Mansfield Library up at the end. It's kind of a long walk to get your books, but and you might need a snorkel or scuba gear when you're up there because we're going to fill it with water so we can run the university. But that's another analogy that you can sort of think about in terms of the scale of if we were to run the university on hydro. Okay. All right, so here's another shot. And if you take a look at the map of Montana, we can see this too. So let's just do this. This is kind of fun. Wow, they just get right down in there, don't they? But we can do something similar right here in Montana and say, well, gosh, there's the Hungry Horse Reservoir just east of Whitefish. Is it something like a dozen dams in Montana? Something like 12 dams of this size in Montana, but there's ours. There's England's version. We've got our own. Yeah, and this guy is just, in my opinion, all kinds of cool. Gordon Butte Pump Storage. And these guys did just get funded. It's a 400 megawatt project, and as I said before, it's a little weird to talk about storage in terms of power. Like normally you would think, like, how much energy am I storing? Well, the convention now is to talk about storage in terms of power. So the Gordon Butte project, which again, $1 billion project, 400 watts, so that's just north of $2 a watt. And it's really hard to build any power plant for that. I mean, so it's cheaper than solar. It's cheaper than coal, cheaper than wind. So $2 a watt. And I don't know if $1 billion's the final price tag or not. They're probably going to need more money as they get on there. But this technology that we're seeing in the textbook is happening right now in Montana. And these guys, Soroka, and this is the one firm that I know pretty well, and it would get much better than Carl Borquist. He's an attorney, and really most of the heavy lifting on this project was getting through all the legal snags and hurdles and the water rights and all that. So I've known Carl for 3 or 4 years now, and it's just really a thrill to see this thing finally come into work. I don't know these other guys, but Borquist has been right out in front of it. So there they are. It's Gordon Butte, and it's it's kind of. Yeah, it's going to be southeast of here. It's kind of, I want to say it's kind of equidistant from Helena and Bozeman. Yeah, I think if we go there and we go out to maps, it might show us exactly. If we did field trips, we would go. Yeah, Gordon Butte. Let's just do Gordon Butte. And really, the driver, though, and this is where integration becomes that much more important, is yeah. So yeah, there's Helena. Here's Bozeman. It's almost equidistant from Helena, Bozeman, and Billings. Yeah, and what they wanted to do, they wanted to develop wind in Montana. Well, and again, here comes the storage problem. If there's no demand, Las Vegas is a long way from Gordon Butte. Seattle's a long way from Gordon Butte. So you pump it uphill when there's low demand, and yeah. So just really in your mind's eye, just replace this thermal plant with a bunch of wind turbines is what you're doing. Yeah. And I misquoted these guys a couple times. I quoted it as an 800 megawatt system, but it's their turbines are 400 and their pumps are 400.
So in terms of like the size of the city that could support, what would that be?
400 megawatts. If it were just electricity, why is my brain not so good at math anymore? Let me do it this way. So yeah, so it's 4,000 kilowatts.
Yeah.
No, it's 400 megawatts, right? So that's 400,000 kilowatts. So yeah, if it was just electricity and each house is a kilowatt, 400,000 homes.
Oh,
Yeah, 400,000
Pretty
homes.
big
Yeah,
capacity
yeah. And typically, the capacity of each wind turbine is, a standard wind turbine now is 2 megawatts. So that would be, 200 turbines. Obviously, they're not spinning all the time, but you could imagine 200 turbines going full tilt could run all of the pumps to run that 400 megawatt system. So just imagine 400 200 2-megawatt turbines running that 400 megawatt plant.
So that's like definitely multiple cities in Montana.
It support half of Montana.
Support half of Montana. Yeah, yeah, yeah. Or a borough in Manhattan. Yeah, with electricity. Yeah.
Yeah, and it seems like this facility is pretty small, so in terms of like ecological impact, it's pretty minimal for this sort of amount of.
Yeah, you could make that argument. You're like, gosh, look where these guys are. They're they're way out here. There's not really a whole lot of you're not wrecking the forest. You're not wrecking the rivers.
And the footprint's small compared to the size of the people that you're
Yeah.
providing energy.
This is true. You can see they're already doing some. So there were a few battles with the farmers and the irrigation, but their argument is like, hey, when all this water is coming down, we're going to be capturing it. We actually have water security, and the water can be used twice. I mean, the water can be used for power and for agriculture.
So how does that have to do with like, like Northwestern Energy has a monopoly on utilities in Montana, so I know that there's issues with like people trying to develop solar that it's hard to do, so are they like interested in buying some of it, or?
I asked that exact question to Bob Rowe 2 weeks ago, and he said this is not a, so remember, the utility in general sits between the primary energy and the consumer. They're just the pipe. They did buy the dams so that they could control the rates, so that is now part of their infrastructure. This is not a Northwestern Energy project, but Northwestern Energy has the ability or option to purchase from this at fair market values.
Yeah.
So they got outside investors together, permitted, and now away we go.
So then if Northwestern doesn't buy energy from them, then can they, there's no way for them to sell to consumers in Montana, or is there?
I don't know that question. I don't know the answer. Where they could, I mean, yeah, I wish I knew the answer. I don't know.
Because
Yeah.
they control the power lines.
They don't. Northwestern Energy does not control all the power lines. They do a lot of it, but they are responsible for monitoring the entire grid here. Yeah.
I'm just not quite clear on why it is that they're sort of like allowed to maintain this monopoly and other companies can't come in and say like, well, we're going to sell this power.
Well, if you live outside of city limits, you will be on a co-op instead, and so they don't have a complete monopoly. They only have a monopoly on municipalities.
Yeah.
Yeah.
But this company can't like come into Missoula and say like, we're going to start selling our energy to you here.
That's a good. That's actually a great question. And one thing I would like to do with my company I'm starting right now is say, hey, we only want to buy renewable electrons, and it comes at a premium because things like this. New projects come online, and that's where I want my money to go. I want my money to go towards renewable development.
It seems like if your only choice when you live in a city is to buy from Northwestern, there's limited incentive for them to buy renewable or to do what the consumers want because you have no other choice.
Yeah, I know they do have a green program where you can pay a premium. In general, and I think some of that money, I mean, for better or worse, I mean, Northwestern Energy is doing a $1 million solar project here, so it could be like, hey, that's where your extra 2 cents went off to that development. So, they're kind of forced to speak out of both sides of their mouths. They like it or not, they become this political, in the political crosshairs. So, all right, I'll let you guys go. I got to go too.